Curve sketching is actually an aggregation of several analysis steps, and I think you can well prepare this type of exercise so that it shouldn't be a big problem during an exam. Of course, teachers and professors usually tend to build in some difficulties, but that's why it's very important for you at least to know the procedure in principle so that you can concentrate on those difficulties and that the standard procedure won't be any problem for you. So basically, the curve sketching consists of 7 points. So first one, you should think about the derivations, or you should even maybe show first, second, third derivation. And the second point is talk about symmetry. Does the function have some sort of symmetry? For example, I had it earlier here somewhere. Any symmetry, for example, symmetry to the y-axis or symmetry to some point. For example, in this case, you can easily see that we have some symmetry here, this function, and we have some symmetry maybe in this function. Usually, function is always the symmetry is always compared to the y-axis or to the point 0, 0. Then what else? We have zeros. So where does the function cross the x-axis? And what else we have? We have critical points. I already present in another video. So critical points are always 2 steps. You should be familiar with these. So we have a necessary condition and we have a sufficient condition, right? First is the first derivation has to equal 0. Second, the sufficient condition is second derivation does not equal 0. When it equals 0, we have to do some further analysis, which is related to the limit. But if it does not equal 0 but the necessary condition is fulfilled, then we can already say, okay, it's either minimum or maximum. So this is critical points. This shouldn't be a problem. And then what else we have? Inflection points. Inflection points is the same as critical points, just that we don't have, like, as in this case, we don't have f with like 1 stroke, or here f with 2 strokes, but we have here f with 2 strokes and here f with 3 strokes. But it's exactly the same, so instead of taking the first derivation, set 0, we take the second derivation, set 0. Instead of the second derivation, in this case, we take the third derivation and say it shouldn't equal 0. Then we can apply these 2 rules, and if it equals 0, we have to do some further analysis to find out what kind of point it is, whether it's some sort of this point, or whether it's maybe some other, maybe this is maximum, maybe this is minimum. This we have to find out with the specific limit analysis. And last but not least, after the inflection points, you should talk about you should show some visualization of the function. And it depends on what your teacher or professor wants, whether he or she wants some kind of rough draft, or whether it should be already quite detailed, or whether just because the function can do a lot of things, so whether it should just show the characteristics, or whether it should show a lot more. It depends. And in this case, you should also ask your teacher or professor what you should really draw, how specific it should be, not to make any mistakes, in order not to lose any points in an exam. This is important. But I would suggest for you to practice this basic curve sketching so that the standard procedure is definitely not the problem in the exam, that you can focus on the problematic areas where you need a little bit more time and calculation. So I will show you in the following clip how it works. Hi guys, I'm going to explain you curve sketching, how it works, and it's quite easy. I think curve sketching is an aggregation actually of several analysis steps. It means how to analyze a function and to be able to tell some characteristics of a function. Okay, so the way it works is we have 7 steps. So I just explain the 7 steps. First step is derivations. Second step is symmetry. Third step is behavior means the behavior of the function when x goes towards plus or minus infinity. Fourth step is zeros. The fifth step is critical points. The sixth step is inflection points. And last but not least, we need some kind of draft or diagrams and something to visualize the function. Okay, how it works is derivations is quite easy, just first, second and third. Third we need for inflection points. And symmetry, we can check whether the function has some symmetry to the y-axis or to the origin. Behavior is like we look at the limit. Is there any limit? Zeros, we set the zero. We say like the function equals 0, and then we calculate the x where this is possible. Fifth step, critical points. It's actually quite a common problem. Critical points and inflection points is almost the same. I will explain later. The thing about a draft, I think it depends, but I tend to do the draft at the beginning of the curve sketching to have an impression and always to be able to check at each step whether this could be possible or maybe I did some mistake during the calculations. I can always check. So, but it depends on your habit, what you like or what your teacher taught you how to do it. So we just show how it works with an example, best way. So function, we have this function. Okay, minus 18x to the power of 4 minus 14 to the power of 2. This is the function. So we start with, if you remember, derivations. 1. Derivations. In this case, okay, we might need a calculator. Minus 18 to the power of 4. This derivative is maybe a little bit... Okay, if we don't have a calculator, we would be able to do it, but in this case I have a calculator, so we use it. Minus 18 times 4, minus 72. X to the power of 3, minus 28x. And there we are. Next one. Second derivation is, okay, again, if we have a calculator, it's much easier. Minus 216. Now x to the power of 2 minus 28. And what's the third derivation? What does it look like? 216. Okay, this is easy. 400. Okay. 32. Yes, 432. Minus 432x. So we have now 3 derivations and we are going to need them later. But I forgot what I usually always do before I start with curve sketching is if I have a function like this, how does it look like? So I see there is a 4 and there's a 2. Power to the power of 4 to the power of 2 at the x, and then I can say probably it looks something like, okay, maybe I do 2 drafts. First I want to talk about parabolas. A parabola like x to the power of 2 looks something like this. If I put a minus before the x to the power of 2, it looks, okay, this is plus, but if I have a minus, then it looks, it just, it's like, switched, it looks like this. Yeah, this should be 0. So it looks like this is minus x to the power of 2. It's turned upside down. And a function, when it has a to the power of 4, like x to the power of 4, looks very similar to this parabola. And if I put a minus before the x to the power of 4, it looks very similar to a sort of upside down parabola. So I can be pretty sure in this case, if I have 2 minus there, or I have, I have x to the power of 4, which is negative. I have x to the power of 2, which is also negative, then it looks, there's a high probability that it looks something like this. Maybe it looks a little bit wider, or a little bit smaller, something like this. It can also be that it has like something in between, does something strange at the left or at the right. But something like this it has to look, definitely. So you see, as a rough draft, I say something like this. Maybe it has something here and here, does some strange things, but it's not important to know it. Before we calculate it, it's just as a rough draft. So we can say probably looks like something like this. Just to know, just to keep in mind when we calculate that it's not something like or or a linear function like linear function. This is not our function. Our function looks something like this, okay? And keeping this in mind, we can continue and always check whether we are on the right track or not. So for the second step, we have to remember symmetry, how to calculate symmetry to the y-axis and how to calculate symmetry to the origin. So just to remember, symmetry to y-axis means what? So we have, for example, we have a function with symmetry to y-axis. As I just explained earlier here, the parabola looks something like this. And there we have a symmetry to the y-axis. And what does it mean? How to explain it mathematically? So without actually knowing the formula, we can just create it by looking at this picture. So we have the values on the right hand side of the y-axis are the same as on the left. So we see actually it has the equation we are seeking has to be this. So the values on the right hand side are exactly the same as the values on the left hand side. Okay, so this is the equation we need to determine, to prove whether we have symmetry to the y-axis or not. So the same thing we can do with symmetry to the origin. Then we have a function, for example, x to the power of 3. I always forget how it looks like, but it looks positive. If you insert positive values for x, we have something like this, like a parabola, similar. And if we insert negative values, of course, then we have also negative outcomes. So it looks something like this, right? So in this case, we have symmetry to the origin. And what is the mathematical description of this case? It is, we have on the right hand side, we have values. And these values are the same actually as if we would put this branch upside down. So we would put it like this. Or we can also say we put the right branch upside down like this. So we can say we have the values of negative x are the same as the negative values of positive x. Understood? It's actually quite easy. You just have to memorize like x to the power of 2, x to the power of 3, then you can build these two equations you need for symmetry. So you don't actually have to learn everything by heart. You just have to understand what does it mean if I have symmetry to the y-axis, what does it mean if I have symmetry to the origin. So it's not too difficult, and in this case we assume that we have symmetry to the y-axis. Of course, symmetry to origin is impossible in this case. We can see from the drafts we just have a try. We try symmetry to y-axis, which would be f. So we need f on the left side and f of negative x on the right side. So f of x is we're running out of space here. So fx is minus 18x to the power of 4 minus 14x to the power of 2 equals the same, but we insert negative x. So we have minus 18 negative x to the power of 4 minus 14 negative x to the power of 2, and we say this is f of negative x, right? This is what we said earlier, how to prove symmetry to the y-axis. And then we see actually it is quite the same, because negative x to the power of 4 minus 1 to the power of 4 is what? Minus times minus is positive. Positive times minus is positive, so it's actually the same. We have minus 18 x to the power of 4 minus, and here the same thing, minus times minus is positive, so minus 14 x to the power of 2. And then we can say, okay, this is the proof. The function is actually as I assumed, so my draft is correct, at least concerning the symmetry to the y-axis. So as I assumed, we have symmetry to the y-axis. So that's what we wanted to prove. Great. So, and we can also say it cannot be symmetry to the origin at the same time, of course, otherwise this is impossible. So, third step, doing curve sketching, we want to know something about the behavior. So behavior of, so we say limit x goes to plus infinity of f is what? Plus infinity, if you remember our draft. Plus infinity, what happens? F goes to minus infinity. So we don't have a limit actually. Limit doesn't exist. Let me say f also goes to minus infinity for x. This should be a normal regular error. F goes to minus infinity for x going to positive infinity, and the same thing. Limit if x goes to minus infinity. If you remember our draft, minus infinity, and then what does f do? F goes also to minus infinity. The limit doesn't exist. Now we can say f goes to minus infinity for x going to minus infinity. So behavior of the function is done. Good. The fourth step is zeros. How to find zeros? In this case, actually quite easy. Okay, we have our function and we need to set it 0. So take our function minus 18 x to the power of 4 minus 14 x to the power of 2, set 0. It looks a little bit ugly, but we can say first we divide by 2. So we have minus 9x to the power of 4 minus 7x to the power of 2. equals 0. Then we can say minus 9x to the power of 4. We say plus 7x to the power of 2 equals 7x to the power of 2. And then we see, okay, we could divide by x to the power of 2, but actually we're not allowed except when we say, okay, we know. Let's say first case, or we say, how to say, we say x1 equals 0 and x2 equals 0. Why do I say x1 and x2? I say x1 and x2 equals 0 because we have two x's actually. When you have x to the power of 2, you know, x times x is x to the power of 2, right? So we have two different x's, so we can say one can be 0 and the second can be 0. Okay, so I will explain later why. And then we can divide by x to the power of 2. Then we get 9x to the power of 2 equals 7. And then we can say x to the power of 2 is like divide by minus 9, and we get 7 minus 7 ninth. And we take the square root and we receive x is minus 7 ninth and square root. And there we see, okay, square root of negative number, this does not, actually it does work, it can work, but in this case we say it doesn't, because this would be like complex numbers and we don't deal with that in this case. So square root of a negative number doesn't work in this case. But we remember we already found some solution earlier, x1 equals 0, x2 equals 0. And the thing is, if we have twice the same solution, we have some sort, it's called, it's a boundary point. So it's something like this. So it just, the function touches the x-axis and then it goes in some other direction again. So it doesn't really cross the x-axis. This is important. So we have a boundary point here. But actually for the analysis, okay, we could write. It depends on what is expected in the exercise. In this case, we just wanted to know zeros, so we know at 0 that we have a 0 actually if x equals 0. Okay, so maybe we can calculate a point or something. So it's 0, and if we put 0 in our function, we see, okay, we also have 0. So 0, 0 is a 0. Okay, this is zeros. And so you just continue, we keep everything in mind from this page, and we just continue with the critical points. And this is my preferred step actually, critical points, because it's so easy. We just have to remember critical points, how to calculate. Okay, we have a function. We have a necessary condition, which is first derivation is set 0. We have a sufficient condition, which is the second derivation does not equal 0. If it is greater than 0, we have a minimum. If it is smaller than 0, we have a maximum. So it's quite easy. Just these, this is not really a step, the first one, but these two steps, necessary condition, sufficient condition, and then we know it's quite easy. And derivations we already calculated, so it's actually just a quite easy step. So let's do it. We have the first derivation. Then we need to remember this is minus 72x to the power of 3 minus 28x. So you just transfer the first derivation minus 28x, and then we say this is set 0. There we see, okay, the first solution would be x is 0, so x1 is 0. Then we can divide by x and say minus 72 x to the power of 2 minus 28 equals 0, then we can say plus 28, so 28 to the right side. Then we have minus 72 x to the power of 2 equals 28. Then we say divided by minus 72. Then we have x to the power of 2 is minus 28 divided by 72. And then to solve it, we say we take the square root. So we have finally x is the square root of 28 divided by 72. Then we can see again, we take the square root of a negative number. This does not work. In this case, I mean, in general, there is a solution to it, but not on this level. Just simple curve sketching, not complex numbers. So this doesn't work. And then remember, we had a solution which is x1 equals 0. And this we can further investigate with our sufficient condition. So this was the necessary condition. We set our first derivation 0, then we can calculate some solution to it, and then we need to check the sufficient condition, which is the second derivation does not equal 0, and which is in our case second derivation of x1, 0 is what? Then we need to check again. Second derivation minus 216 x to the power of 2 minus 28. So if we put in a 0, then we receive minus 28. Minus 28 is smaller than 0, so it means we have a maximum. We can also insert the 0 again in our function, and then we see, okay, maximum. Of course, we calculated it earlier. It is at the same time, it is not only a maximum, but it's also a 0, because it's a boundary point. We just calculated it. So the critical points part is finished actually. So we continue right away with the inflection points, which works quite similar. So how to calculate inflection points? Calculating inflection points is actually exactly the same as calculating critical points of the first derivation of a function. So we say we have a function and we have a first derivation, and calculating critical points of the first derivation is like setting the second derivation 0, and we look at third derivation and we say third derivation does not equal 0. So this is actually what we do when we calculate inflection points. So we start with the necessary condition, which is second derivation set 0. What is our second derivation? Okay, we calculated it earlier. It's minus 216 x to the power of 2 minus 28. We just take it to this part, second derivation, minus 216 x to the power of 2 minus 28, and we set that 0. And then we want to know what is the solution to that. Okay, we can just say minus 216 x to the power of 2, we say plus 28 is 28. Then we divide by 216 minus divide by 216, and it is x to the power of 2. 28 divided by 216, don't forget the minus, and then we take the square root. X is minus 28 divided by 216, square root, and we know, okay, square root of a negative number, this does not really work. So we see there are no possible candidates for inflection points. Then we can say, okay, no inflection points. So this part is also solved. So if you remember seventh part, actually in this case would be a little bit difficult maybe, or maybe not. We already calculated, we already thought about a draft. So it possibly looks something like this. So we calculate a 0, we have a boundary point here at 0, 0, and we have also maximum here. We have point symmetry, so it probably looks something like this. I mean, maybe the branch is a little bit wider. This would be possible, but there are no critical points at the right or at the left of the function. And actually, this is not too difficult, this example. It always works the same, even if you have functions which look really horrible. Curve sketching works always the same. So you just remember critical points, inflection points is almost the same. So we need derivations for that. Zeros is also, that's not too difficult to remember. 0, you just set the function 0, then behavior, you just check what is the function doing. Therefore a draft is quite useful, and there we saw, okay, in both cases, minus x plus x goes to infinity. We have the function going to minus infinity. Symmetry, you also don't really have to remember the formula, you just can imagine what does symmetry to y-axis mean, what does symmetry to origin mean, and then you can derivate the formulas. You can also memorize it, then you're maybe a little bit faster, especially in exams. This may be an advantage if you know those formulas by heart, but if not, if you forget it, no problem, just imagine how it works. Symmetry to y-axis, symmetry to origin, and derivations is a point you should absolutely know. You should be sure about how to derivate, how to differentiate functions, and then it's not really a problem. So also, depending on whether you're in high school or in college, is always the same. The procedure is always the same. The functions may look a little bit more difficult, but the procedure is always the same, and also you don't really have to memorize a lot of things. You just should be able to do derivations and to be able. What helps me a lot is, for example, that I know, okay, a parabola looks something like this. It's like x to the power of 2. And I know also x to the power of 3 looks something like this, and by this I can also, or for example, I have x looks something like this, and by these things, if you know how functions look like, how typical functions look like, then you can already imagine how the function you get in an exercise or in an exam looks like. So this is how it works. This is curve sketching. Thanks for watching. Practice makes perfect. Further exercises with solutions you can find on my website, which is www.worksheets.com.